Everybody. All right, so quick thing on Tuesday, as you hopefully know at this point, is the midterm. If you haven't started at this point, please realize that you're late in the game and get started as soon as possible. Last time we talked about regularization, and I showed you that the L2 regularizer is basically saying I have a ball. Oh wait, this is not on. Is this on? No. Is it on now? Better? Yeah. L2 regularizer says you have a ball around the origin, and maybe let me move this up after all. So the L2 regularizer is a ball around the origin, and what you're essentially saying is, you say the solution has to lie within this ball, and this is how you control complexity. Please close your laptop, thank you. This is how you control complexity. So essentially what you want to avoid is that you get a really, really complicated solution where some values are really, really large and others are really, really small. So if you shrink everything, it basically has to come up with some simpler solution. That's the ultimate intuition. And you're restricting the space. Right? Instead of actually finding a solution anywhere in the space, you just say, well, it has to be lie within this ball. And so you try to minimize some function. Let's say this is my function, here's the minimum. Right? So ideally, if I didn't have any constraints, I would end up here. But my worry is that that could overfit to the training data. So what I'm saying is, find a solution to this function, but stay close to 0. And that typically helps with generalization, gives you a better estimate, for your test data. And also actually, that's actually what the map estimate gives you if you have a prior, Gaussian prior over your vector. Another norm, another regularizer that's just as popular is the L1 norm. So the L1 norm is the following. You just regularize lambda times the absolute value of W. And if you draw that as the same kind of image, what you get is not a ball, it's called the L1 ball. The L1 ball actually is not a ball at all, it has corners. It looks like this. Right? This is the L1 ball. It's kind of like a diamond. Right? And so you're restricting, you're trying to find the optimal solution, and you're restricting your set to be inside this L1 ball. That's the idea. Can anyone imagine what are the advantages of the L1 ball? What are the properties of the L1 ball? Like, why would you do this? Why would you not always use a circle? Any ideas? Yeah?
So like a circle is uniform distance from a point, but a cube or whatever would be like within the range 0 to 1.
Well, this lambda basically defines how big that area is, right? So you can make it as large as you want. It doesn't have to be uniform. Yeah? That's right, you increase the sparsity. That's exactly right. So what it does, and let me explain this for everybody else. What happens is, let's say you're minimizing this function, right? And let's say this function is up here. The minimum is up here. Okay, so ideally, what would you want, right? This here is my W1 value, this is my W2 value. The best thing would be to have W2 pretty large and W1 some small value. Okay, so that's the optimal solution if no constraint was enforced. Now I'm enforcing my L1 constraint, and now if you look at this objective, let's say this objective function looks something like this, right? What you will see that actually the optimal point will be exactly this corner here. Right? Because it has these pointy edges, the pointy edges kind of can penetrate this function a little bit further. And so the optimal solution will be this value here. And what does that mean? I crank up W2 as much as I can, and I set W1 to 0, not to a small value, to 0. Right? And so that's what ends up happening here. In L2, you don't really see this. In L2, you would end up somewhere here, pretty, pretty close. Like you would have a very, very small value of W1, but it wouldn't be 0. And the reason people really, really like setting things literally to 0 is because then you can rule out that whatever feature W1 whatever dimension that corresponds to, contributed anything to the prediction. So if you make predictions in biology, and you want to know, for example, here's my DNA or something, right? And I want to predict, does a person have, is likely to get cancer, yes or no? What I would love, right, if most of the weights are actually zeros. If I can do well by a prediction well, and then actually most of my weights are zero, then I know all of these things actually didn't actually contribute to the prediction, right? And that makes it much, much easier for me to understand how the algorithm arrived at the prediction. Okay, so what people, like especially in sciences, people actually care much more about understanding the prediction than actually the actual prediction itself. And so therefore they love these sparse vectors, that when a lot of things is set to zero. And so with very high dimensions, what you will see is that actually, in 3 dimensions, this kind of, goes out of the, out of here. And so these entire edges all have W1, 0. So in high dimensional spaces, this thing consists of many, many edges, and almost all of these edges have the majority of the weights set to 0. So your answer will almost always lie on one of these, and so you will get a very, very sparse answer. Your weight vector will set almost all weights to 0. Yes?
So why, if the goal is to reduce the cost of testing variables and it can be very little, why not use the arguably better sphere model, and then afterwards you run a cost analysis on your classifier on each on each piece of information for your classifier and decide how much are willing to that feels
Right, so what this thing is going to do is this will set something non-zero to every single dimension. Right? So I guess what you're saying is why not train this and then just look at the largest weights or something and see, the problem is you don't know, a small weight may actually still contribute a lot, right? Only once it's 0, it's really kind of off. It's switched off. People do this occasionally, that they actually then look at the top weights, but why not just use L1 regularization? There's actually, to be honest, the optimization is more annoying with L1 regularization, but ultimately the predictive power is usually not worse. Is that going to answer your question? The nice thing actually, and we won't get into this now, but actually if you do L1 regularization, one thing you can do, you can actually solve in closed form for the values of lambda such that exactly the first feature becomes non-zero, the second feature becomes non-zero, and so on. So just to make this clear, if my lambda is very, very large, then this little diamond is going to be really, really tiny, and almost certainly I will sit in exactly one corner, so only a single feature will be non-zero. And that also intuitively makes sense. If you think about your loss function, there's going to be a single feature that's most important to predicting the label. If it can only spend very, very little weight, what it's going to do, it's going to put all the weight on that one feature. Right? So that's what the L1 regularizer does. And so basically one thing people do is they kind of grow this ball slowly, essentially lowering lambda, and then kind of see which feature is picked first, which features picked second, and so on. Any questions? One downside of the L1 regularizer is that it's not strictly convex. So that means there's actually, you could have, for example, imagine you have 2 features that are identical. Then it doesn't matter how much weight you put on one or the other. And you could put all the weight on one feature, all the weight on the other feature, or half on both, or any combination thereof. And they're all exactly the same solution. That's one downside, and that's annoying. So what people do in practice, and this is called the elastic net, is that you do a little bit of both. You do lambda L1 plus mu L2. And where mu is very, very small. So if you do this, then actually because this here is strictly convex, there's a unique solution. There cannot be multiple solutions. Oh, sorry, there's a, yeah. Mm-hmm. How do you, sorry? This constraint basically says minimize my loss, subject to is less equal some budget. And this budget corresponds to lambda. So last lecture I said that is equivalent to saying minimize L of W plus lambda times W. Those are the same, that's the same thing, it's the same optimization problem. This is just the Lagrangian formulation. So I can go back and forth between these. It's just these are nicer because now actually you can draw the set and you say you have to lie inside the set, lie inside the set. But those two are exactly the same thing. In fact, actually, if you solve this problem, then if you just take the norm of W, that is exactly B. And if you think about it, what is the absolute value, right? Like absolute value of W equals the sum I W, let's call this alpha W. So basically I'm penalizing every single W the same way, every single dimension the same amount. So I'm saying I try to find a simple solution. That's my goal. That's why I'm regularizing. I'm saying, you don't just minimize the loss. You minimize the loss, but find a simple solution. Here defined implicitly as saying the sum of all the weights must not be larger than B. But it's okay to put all the weight on one dimension. That's okay. That's not more complicated than putting a little bit of weight on all the different dimensions, right? That's okay. Here, I do something else. Here I say it's the sum of alpha W alpha squared. So here I'm saying if I put all my weight on one dimension, that's worse than putting a little bit of weight on all the other, on every single dimension, right? Because I'm squaring, right? So if I put, my one weight really, really large, I square this, that's a lot more than many, many small squares. Right? So it's a different definition of complexity. And so this definition of complexity basically leads to, the classifier putting all its weight on a few features. And that's very informative. Has the disadvantage that it's more brittle, right? So if you, for example, imagine you have a self-driving car or something, try to classify something, and it put all its weight on a few sensors. If these sensors then drop out, then actually, your prediction is off. Whereas this one can be more robust because it spreads out the weight more. Any questions? Yeah? It does not solve your differentiability problem. What the elastic net solves is that one thing you could do is you could actually, if you have two features that are highly correlated, then you could put weight on one feature, on the other feature, on both features. And that's the same thing according to this thing. Whereas this thing only has a unique solution. Imagine you have two identical features. The optimal solution in terms of the L2 norm is to put the same amount of weight on both. Right? The moment one would be larger, because it increases quadratically, you're actually paying more for that. So that's what that does. So the elasticness basically kind of combines the robustness of the solution with the ability for L1 norm to actually identify features. Yeah? Same thing. Yeah. Any more questions about this? Yeah? Yeah, but the problem, so his answer is saying the following. Imagine I have two identical features. Wouldn't it be the best thing if the answer would be to just set one to 0 and set the other one to a large value? But that's not what the L1 norm is doing, right? The L1 norm, you have no idea what you're doing because they're all exactly the same, right? So depending on your implementation. And that's what scares people, right? Because two people run basically the same, optimize the same optimization problem, they get different results, and you don't know which one is right? What the problem is. People would like to have deterministic answers. And so by doing this, now you have, now if you run this and I run this, we must get the same solution, no matter what solver we're using. But if you use MATLAB or Python, it doesn't matter, right? Yeah?
So you use it to just select the features, and you actually fit the model.
You fit your model, you minimize the model, but you add this complexity penalty, basically, right? And this serves two purposes. A, it avoids overfitting. And this is the Bayes variance trade-off, which is the first lecture after the midterm. And the second thing is that you will also discover which features are responsible for the prediction.
Isn't it better because it shrinks the weights?
Right, it shrinks the weights, yes. So, okay, good. So he's asking a very good question. He's saying, wait 1 second. If I'm a biologist, then all I care about is basically, the first thing I care about is which features are useful, but then actually I really want to have a good predictor. Now these things are in conflict with each other, right? So I have to make a tight budget B. I say I want to have my classifier inside this small area, right? That's good, because that will tell me which features are responsible for the prediction. It will set 0 to most features. But those that I'm selecting, it will also shrink those, right? Because it will, in this case, it will put all the weight on W2, but ideally W2 should be this value up here, right? So I want to learn that W1 is maybe not relevant, or W3 maybe is not relevant at all, right? But I still actually don't want to cramp W2 style here too much. And so he's saying, why don't we just run this first, then we identify which features are useful, and then we run without regularization, or with L2 regularization on with these features. And that's what people actually do in practice. So if you'd invented it 20 years ago, you'd be famous now. Okay, any more questions? That was kind of the end of ERM. Please look at the notes. I wrote down two or three famous cases. One is called lasso. Lasso is squared loss. And the other one is elastic net if you add an L2 regularizer to it. So if people refer to lasso or elastic net, this is what these are. So basically just the square loss with either L1 regularizer, that's lasso, and L1 and L2 is elastic net. And then we also have SVM and of course logistic regression you already know. Maybe I show you a very, very quick demo for a few seconds, and then I actually want to do a little bit of review for the exam, just to get you guys ready. Okay, what I want to show you now, it's a small data set iron. I don't think you've seen it yet. It's a small, some data set actually from life sciences. And what you see here is, let me just explain this. Just pay attention for a second, guys. So what I show you here is basically if I run the classifier, there's a squared loss with L1 regularization. That's called lasso. And I crank up a lower lambda. So if lambda is really, really large, this here is the first solution. So the x-axis here is basically whenever I kind of lower my lambda just enough such that one more feature becomes unlocked. Okay? So if my lambda is infinitely large, then every feature is 0. Okay? So everything is at 0. And what you see here, these lines are the weights associated with the different features. So if I lower my lambda a little bit, the first weight shoots up. That's the first feature that it picks. Okay, so basically at the beginning, right here, I basically allow it just a little bit of weight, right, to distribute over the weight vector. And what it does, it picks one feature and puts all the weight on that one. Right, so that's the most important feature. And then I lower lambda further, and what it does, it keeps increasing that feature, but it also increases another one. That's the second one. All right. And so these are some features. They're not necessarily dimension 1 or 2. These are just over the vector, right? Here, you see the same thing. This here is the weight vector. So what you see here is the first weight is all green, so that's 0. Everything is 0. And then the next row is the weight vector. It's like the weight here is incorporated as color. So you basically see here, the first value up here, that's non-zero. That's the first feature that basically some weight assigned to. And then as we keep to the right, what you see is that basically the features get more and more pronounced, right? More and more weight is distributed across the different features. And so here, that's the same graph as this one. This is just basically, you see the value, as negative or positive points here along these lines. So here at the end, basically, what this line tells you is that this particular feature has a value of -2 almost, minus 0.2. Okay, does the graph make sense? Raise your hand if the graph makes sense. Okay, good. And what you see here on the top right is the error. And one thing you can see is as I'm lowering my lambda, right, the training error, the loss goes down very, very nicely, right? That makes sense, right? Because actually now I'm not constraining myself into a ball anymore, right? At the beginning I'm constrained this very, very tiny ball. Now I'm growing this. So eventually I basically, I can get closer and closer to the actual minimum. What you ever see is when you look at the test error, and that's the yellow line. Let's look at the training error first. Training error is the red line. That also goes down nicely. But the yellow line is the test error, and that actually goes down up to here, and then it goes back up again, right? So actually the lowest value is actually at 0.5, with 5 features, so here. So you only need 5 features, right, to do really well on the test set. Afterwards, the other features, they help you on the training set, but they don't help you on the test set anymore, okay? And that's exactly what the biologists want to know. They want to know which 5 features, right, are the ones that really help me on the test set, right? Because those are the ones that really generalize, right? The other ones are just fitting noise, right? Something that's specific to that particular data set, okay? So when you work with biologists, or in life sciences, make these kind of graphs, then find the cutoff point, and they're going to get really, really excited when you then tell them it's these 3 genes or something that explained actually everything on my, the entire test error in my test data, or the accuracy of my test data can be explained just by these 5 genes or something, or this protein, or something like this. Any questions? Yeah? Oh yeah, well, you got me there. I can't remember. It was something with iron. I don't remember if it's like in the blood or something. I can't remember. Sorry. So that's the problem. I just think about the abstract data. And yeah. Lambda, this is actually, what this here is the number of features that are non-zero. So I always decrease my lambda until the next feature basically becomes non-zero. And turns out actually there's an algorithm called least angle regression that we won't cover in this class. But that algorithm actually tells you exactly what the next value for lambda should be. So it's actually, you can solve that in closed form. It's correlated with B, but it's basically, that's right. It's just that it's somewhat, there may be different gaps. B may suddenly increase a lot until you get the first feature, then it may just go a little bit further up to the second feature, right? So it's really the number of non-zero features. That's what the x-axis is. But yes, you're right. As that goes to the right, B goes up as well. It's just not linear, right? Yeah. So the loss is the actual loss that I'm minimizing is the squared error. But in this case, actually, it's a classification problem. So actually have a training error as well. Right? And those are not the same thing. So if you actually see that the loss keeps going down, but the training error goes up, that means I'm overfitting to the loss function. Right? I'm putting too much energy trying to get the square loss right when I really care about is the training error. Okay, any more questions? Yeah. Yeah, if you only care about prediction, then I guess this is like looking at the feature vector is less interesting, right? Also may help you debug things. You may still want to use lambda, right? Because here the best test error is actually at lambda, at 5 features. So you still want to do regularization. Right? So otherwise you don't know when you're fitting noise, when you're just memorizing training data, and when you're still generalizing. Any more questions about regularization? By the way, it turned out that actually is a funny thing that elastic net, which is, I guess, what people typically use here, actually can be solved. It's the same thing as an SVM. There's a very interesting relationship that actually a student of mine discovered 2 years ago. We call it Sven. But you can actually reduce elastic net exactly to support vector machines. So for any problem of this kind, you can actually construct a new artificial problem that has no meaning. And if you feed that into an SVM, the weight vector is exactly the one that you get here. And so the nice thing is SVMs can be solved much faster. All right, what I want to do today is a little review. Okay, good. So I thought we make two teams. So how about undergrads against grad students? Does that sound good? Who is undergrads? Raise your hand. Who are grad students? Oh, that's rough. Do we have anyone who's neither? You add them to the grad students. How should we? Are the grad students? Are you willing to take the challenge? Yes. Okay. Okay. Good. All right. Let's do this. Undergrads. This is grads.
What do we get if you win?
What do you get if you? Oh, street bragging rights.
I demand an extra point of
Okay, does this work? Yes, this works. Okay, good. Okay, so because the grad students are few, so the way it works, do people know Jeopardy?
yes.
Yeah. Yes? Okay, great. I don't, but you can tell me how it works. So I guess the people bid on these fields, and then this is how many points they get if they get it right. So the way it works is someone says, for example, SVMs for 40. Questions get get harder as you go to the higher points. And then I read the question. The moment I'm done reading, anyone can answer it. You raise your hand and you make a loud buzzer noise. It goes like, eh. All right? So maybe let's practice that for a second. Okay, 1, 2, 3. Good, good. Don't be shy. Maybe each individual can only answer 2 questions. Let's say do this. Undergrads can only say 2 questions. Grad students can only answer 4 questions. All right, that's fair. Let's put some regularization on. Okay. Grad students go first. Who wants to go first? Any grad student? You don't have to answer a question. You just have to say which field I should read. It's pretty safe. Yeah? Sorry? k-NN for 10. Okay, he's playing it safe. All right, here we go. The error of 1 nearest neighbor classifier is at least as bad as twice the error of the Bayes optimal classifier as n goes to infinity. Who raised their hands? I heard someone. Was it you? Sorry? True or false? True?
It's true. It's false. Because it's at most.
Good, okay. Are the undergrad or grad?
Undergrad.
Okay, good. 10 points. Yeah, it's at most as bad, right? Otherwise, it wouldn't be not as useful of a bound, right? Oh, you can barely see this. It's supposed to be dark. Okay.
Yeah, we can see it.
Okay. You can pick the next one.
Naïve Bayes for 50.
Naïve Bayes for 50, all right. Ready? Go. Oh, here we go. When is the Naïve Bayes decision boundary identical to logistic regression? Okay, good.
When we are assuming the Gaussian distribution, like when the data is assumed to be generated by a Gaussian distribution.
You almost got it. Can someone help him? I allow some other grad students to help him. You're undergrad or grad? You're grad, okay. Now the undergrad says. That's it. The undergrad, yeah?
So it's when the probability distribution of the probability given the label is Gaussian distribution.
That's exactly right, right? So it's not when we assume it, when it's actually true, right? That's what it is. Yeah, I will post those. Yeah, okay. Okay, you can ask the person who just answered the question. You can ask the next one. You can pick the next one.
Go with SVM50.
SVM50, all right. Ready? Go. Why shouldn't you incorporate the bias as a constant feature when working with SVMs? just make this clear, when we had a perceptual algorithm, we just incorporate the bias as a constant feature, right? We just added a feature of 1. Just, why can't you do that with the SVM? Wait, I didn't hear a buzzer now. That has to, come on. Okay, good.
I think it's related to the inequality being less than 1, because if the inequality actually has to be less than gamma, which is the separating boundary, and you divide the entire equation by gamma.
Nope. Undergrad or grad? Grad. Okay, so the undergrads get a chance to answer it. There's 50 points. Why can't you do this? So if I would just absorb the, yeah. Ah, exactly. That's it. That's it. Right. Undergrad, I presume. Oh boy.
What was the answer?
So the answer was that because we're minimizing W transpose W, right? That's actually, we're maximizing the margin. But a crucial part of this is that we are not minimizing B squared. Right? So if we would actually minimize W transpose W, but you absorb the B in there, right? Then that would be the same thing as minimizing W transpose W plus B squared in your objective. Right? And that's actually not maximizing the margin. That's actually saying I'm maximizing the margin plus I want my decision boundary close to 0. Right? Which is not what SVMs do. Does that make sense? So B actually has to be free. Right? B is not minimized. Very nice. Okay, next question. Which one do you, oh wait, let me just.
I have a question about the logistic regression.
Yeah, sure.
Is it also the constraint that the standard deviation across the labels has to be?
So who's talking? Oh yeah.
Is it, because if you're using the Naïve Bayes assumption, right, and then for it to be exactly the same as the logistic regression, doesn't the extra constraint that the sigma A's have to be the same across all the different features? Isn't that an extra constraint that has to be?
That's right. That's part of that constraint. That's right. For it to actually become a linear classifier. Yeah, that's right.
So if all the features itself.
So it's Gaussian distributed with the same variance across both countries, classes. Sorry. Yeah. Natasha, right? You can pick the next one. k-NN 50. You guys, I like it. You go for the big ones. All right. Ready, set, go. How would you modify the k-NNs algorithm for regression? Someone? Okay, good. Okay, sure. A grad or undergrad? Undergrad. This point, you've scared the grad students so much they're not even going to say anything. Yes, exactly right. So one thing you can do is you can just take an average of the k-nearest neighbors, right? And that gives you a value. And so even better, actually, if you take a weighted average. So actually, if you just take, assign a weight to every single point. So you do the following. I sum over all my neighbors, I element of my neighbors, wi times yi, and then I normalize the whole thing. Sum over I element of n wi. Right? So they have to sum to 1. Otherwise, it's not a weighted average. And so, one thing you could, for example, have this, this weight wi could be the distance, 1 over the distance, x minus xi. Or one thing that people often pick is the exponentiated. So basically what you do is you want to give less weight to points that are further away. That's all. Now you can define your own weighing function. Typically that improves the results. All right. Next question. General 50? All right, ready? Go. For each algorithm, name one assumption that it makes on the data. k-NNs, neighbors, Naïve Bayes, logistic regression, and SVM. Arthur? Okay, good.
k-NN, points that are close to each other have the same class. Naïve Bayes, each feature of your feature vector are independent from each other. Logistic regression.
No,
Wait. Oh, yeah.
Okay, keep going. Right, independent given the class label. Very, very important. Yes, conditionally independent.
Logistic regression is that your two classes are both normally distributed based on given the feature vector. And standard SVM is that your data is linearly separable. Wait.
Who wants to help him? You're almost there. I mean, it's very, very close. So, I mean, I don't know. Okay, you know what? I give you half the points. How about this? In part, also to motivate the grad students to give them 25. Here we go. We can't just beat them up. It's like, so yes, k-nearest neighbors, data points that are close. Similar points have similar labels. That's a good one. Naïve Bayes, features are conditionally independent, right? Logistic regression, you said the right thing. Actually, it's actually a little less strict, to be honest. In practice, I would count it because we didn't talk about it in detail. It doesn't have to be a Gaussian distribution. Actually, it also works for any distribution of the exponential family. Gaussian is one of such example. And SVM is linearly separable. Yes, except when you actually have slack variables, and it doesn't have to be, right? Then actually still gives you, gives you a reasonable answer. But on the other hand, the assumption you're making is that a linear classifier, is a good classifier, right? Like you can fit a hyperplane, which is gives you reasonable results, which is a big assumption, right? That could be totally wrong, right? Could be that the function is totally, data set is totally learnable, but with any, you just can't do it with a linear hyperplane, right? So in that sense, let me count it. Another assumption is that a larger margin actually generalizes better. So that'd be something specific to SVMs. Yeah, so, it was basically correct. Okay, good. Arthur, one more? You can pick one.
ERM50.
ERM50, okay, I like it. Which loss function was used in each case? I have three different examples. The squared hinge loss with C very, very small, squared hinge loss with C large, or the exponential loss. That may have been taken from an exam, actually. I'm not sure. Okay, good. Wait, undergrad or grad? Awesome. All right, go for it. Come on, we're all cheering for you. The first one's a really good small c. That's correct. That's correct. Exactly. Perfect. Woohoo! All right, it's the comeback. All right, so just to make a few indication why this is obviously the case. So here, the first one, right? It gets basically everything wrong, right? Like it's horrible, right? The decision boundary is not between these different classes, right? It doesn't care at all about getting the points right. It just cares about having a smiley w. It's a tiny w, which is exactly here. The w, you can't even see it. It's so tiny, right? So that's, basically you have almost a zero loss in front of your constraints, in front of your slack variables. So these two must be the other two. And I guess what you see is that the hinge loss here basically tries to enforce a margin between these two. You see one point is on this side, so that should be here, right? So it basically gives up on that one. That's a lot harder for the exponential loss. It also has to give up on that one, but it will be moved much, much closer to that point just because it gets exponential penalty. All right. SVM for 40, okay. Why is the SVM margin exactly 1 over the norm of W? You have to do the buzzer sound. Okay, good.
Is that the point? Set the value such that the margin is equal on both sides?
No. That's just maximizing the margin will ensure that it's equal on both sides. But the question is, why is it exactly that value? Yeah.
So the actual distance is mod Wx plus v divided by 2W. We assume that mod Wx plus v is equal to 1. We can get it.
That's exactly right. Grad student, undergrad. Grad, all right. You guys are coming back. It's getting exciting. So the answer is very simple. Is the margin is actually W transpose X plus B times I guess, divided by the norm of W. But we, during that motivation, said, well, let's fix the scale of W and B, right, to any particular value. And what do? We fixed it exactly such that it's 1. Right? And this was just to make the optimization problem easier. So essentially, it's the answer is A, because we fixed it that way, or B, it's enforced by the constraints. Right? The constraints basically ensure that this must be the case. And by the way, if you just look at this objective, that's the size of the margin. Now it becomes clear why minimizing W squared actually maximizes the margin. Right? You're basically minimizing this the norm of W here, but the margin is exactly 1 over that. So if you minimize the norm of W, it basically must blow up, right? You're exactly maximizing the margin. All right, which one do you want to pick? ERM for 40. Oh, my grad students told me to make that sound. I don't know what it means. All right. So there's no debate. Oh, shoot, I shouldn't have shown you the question. Before you can actually now bet and number. Wait, this was a grad student, so you can now bet. But who asked that question? Okay, you can now bet as much as, as many points as you want on this. And if you get it right, it will double them. So you got to double, to be honest, the best strategy. But it's your choice. You can. How many points do you want to bet? Everything? You want to go everything? So basically the way it works is you bid a certain number of points, and if you get it right, you double them. If you get it wrong, you lose them. Is that correct? You get nothing.
I'm not sure.
All of it. You got to go all in. That's the optimal strategy. You got to win. Okay, good. You're right. 115. Okay, good. So now only the grad student's allowed to answer, right? But if you get it wrong, you lose everything. Name 2 distinct reasons why you might not be able to use Newton's method on a particular data set independent of convergence. So I'm taking away the one that may not converge. Give me 2 reasons why you may not be able to use Newton's method. Only grad students. Only grad students.
I have one. Let's say one.
You have to do both. Okay, should we do teamwork? Okay, sure. So first one. Okay, first one.
If the loss function is not twice differentiable.
Okay, first one, if the loss function is not twice differentiable. That's correct. Second one, I can think of at least 2 more. Yeah?
If the data is very high dimensional, it might not be able to compute the Hessian.
That's exactly right. Right. So if the data set is really, really high dimensional, it may not be feasible to compute the Hessian. All right, I give you the points. Awesome.
What was the last one? Because you said you had 2 more.
Oh, it may also not be invertible, right? You actually have to invert the Hessian. Okay, now it's getting really, really tight.
I think the graduates are in the lead, I think.
I guess they have 230 and 150. Oh, yeah, they are. This is like the election. It's like unexpected. Don't take it too personal, sorry. All right. Who can pick? I guess that, you were the first one. So
Naïve Bayes 40.
Naïve Bayes 40. All right. Ready, set, go. Map estimation with +1 smoothing in Naïve Bayes with C classes and a categorical distribution with K categories per feature is equivalent to adding how many hallucinated samples to the training set? You got it? Hallucinated. Hallucinated. C? No. Yeah. It's C times K, right? Because for every single class and for everything in category, you have to hallucinate. You assume that you see it at exactly once, right?
Wait, was that a grad or an undergrad?
That was a grad student. Okay, that's how many points? 40. Oh my gosh, the grad students are winning. It was the daily double. That's what it is actually. By the way, that's how Watson actually won. So Watson actually, they knew they had no chance against the human players, the IBM Watson. They're actually much better, the human players. But they knew, one thing they observed by watching the videos is that humans are terrible at betting correctly and actually finding the daily double. And so that was actually so they had an entire team working on two strategies. A, betting optimally for the daily double, which you can actually solve for exactly. And B, the other thing was actually to find the daily double. So daily double is always hidden somewhere. And what they did is they actually analyzed all these past videos and they realized that the distribution is not uniform at all. And so they actually incorporated that in Watson's strategy. And so Watson had a much higher chance of getting the daily double and then actually capitalizing on it. That's actually exactly why it won. Okay, who was this? Oh, it was you. Yeah. Naïve Bayes for 40, all right. Oh, we just had that one, sorry. k-NN for 40, all right. Why does k-NL still perform well on high-dimensional faces and hand-written digits data? Who was the first one? You were the first one, okay.
Because it's not actually, the data is actually not very much with the subject.
That's right, that was 30? 40. All right, so the answer is the data is high dimensional, but that actually is not what matters. Is the dimensional? Sorry, the space is high dimensional, but the data actually intrinsically is not high dimensional. Right? You can even take a low dimensional data and just represent it in some really high dimensional space, make everything else zeros, and then just rotate the space arbitrarily. Then it will look like the data is really high dimensional when it's really not. Right? So k-nearest neighbors won't change. Okay. General for 40, all right. Which algorithm would you expect to result in lower test time classification error? K-nearest neighbors or linear SVM? A, on text classification by topic. B, patient's vital signs. Given the patient's vital signs predict the health status, you have 15 features. Or C, 60,000 handwritten digits classified as 3s versus 8s. So on each one of them, which one do you think will do better? SVM or k-nearest neighbors? Yeah? But we do them out of order. Okay, so SVM, SVM, k-NN. Well, okay, tell me why. If you have a good reason, then I count. Right, I'm with you. I'm with you. The question is B.
Yeah, I guess I was a little well, I guess like here, I just feel like it would be easier to find like a linear like hyperplane rather than like assuming that your neighbors are similar. So I feel like there's not a lot of evidence.
So
I guess when you think
yeah, so the point here is basically that this is very low dimensional data, right? So typically on low dimensional data, linear classifiers do not work well, right? just because there isn't just much space, many options to place a hyperplane. So the first one, definitely linear classifier. Text documents are really high dimensional, right? You always find a good, linear classifiers are amazing at this. But the other two typically are not very high dimensional and tend to have nonlinear decision boundaries. So k-NN tends to work better. How about this? I give you 30. I give you 30 points. And I give 10 to the grad students. All right.
So to sum it up, all up, you'd use k-NN for all of them?
No, not the first one.
Okay. Got
It is a little bit of, sorry? Oh, you're a grad student. I want it to be a tight race, all right. I just leave it at this. I just say, I feel like 10 points. Okay, we only have kind of out of time. Maybe do one last question. So there's the last one. Okay, you can ask the last one. k-NN for 30, all right. True or false? N nearest neighbors on a data set with n training points and d dimensions takes order n times d computation. True? That's a tricky question. This is a setup. This question is a setup. But yeah. Yeah, exactly right. So here's what it is, right? So because usually you're exactly right. So usually the computation is k times d. So it's n times d to find the k nearest neighbors. Actually, plus the bookkeeping of who the k nearest neighbors are, which is some little tree, heap tree. But actually, if you take all the points as your as your neighbors, then actually all you need to, you're basically always predicting the most common label. So you actually don't need to look at your data at all, right? It's a silly classifier. This is a grad student or grad, undergrad or grad? Wait. Grad, okay, good. Well, it was a tie.